Recall how we represent a normal integer in base 10. The number 185 is a representation of 10 power 0 into 5 plus 10 power 1 into 8 plus 10 power 2 into 1. Similarly, in base 2, a number is represented by the summation of each bit of it multiplied by 2 to the power its place, such that the bit in the zeros place is multiplied by 2 to the power 0. The bit in 1's place is multiplied by 2 to the power 1. The bit in 2's place is multiplied by 2 to the power 2, and so on. All these products are then summed to give the number in decimal, that is base 10. To represent fractional numbers, we follow something similar. When you read a binary fraction, it's read such that each bit on the right side of the decimal is multiplied by 2 to the power its corresponding negative power, and the bits on the left side will have normal powers of 2. So 1011.1001 is 11.5625 in decimal. This is a simple enough scheme, but there is a problem. Originally, we could represent 0 to 255 with an unsigned 8-bit number. But now, because of us assigning a fixed point in the middle of a number, our range becomes much smaller. You might say that we can simply add more bits, but say a physicist wants to perform a calculation with a Planck's constant. It would be much easier for him to perform calculations with the scientific format rather than the fixed point format. Similarly, computers need a large number of bits to work with very large and very small numbers in the fixed point format. The floating point system enables representation of both very large and very small numbers without needing enormous amounts of space. Floating point numbers are essentially scientific notation for base 2. To the IEEE 754 floating point number format, floating point numbers are made of 32 or 64 bits depending on their precision. A floating point number of precision 1 contains 32 bits. Instead of using the entire 32 bits to represent one number, we are going to break these bits into 3 parts. The first bit here represents the sign of the number. The next 8 bits represent the exponent, which is 2 to the power of something, while the remaining 23 bits represent the Mantissa, which is the actual body of the number. We use the sign, the Mantissa, and the exponent in an equation like this to construct a floating point number. To get a deeper understanding, let's see how computers construct a floating point number. It would be easier to work this backwards, so let's start with a floating point number. First, let's determine the sign of the number. 0 in the first bit means the number is positive. 1 in the first bit means the number is negative. Then let's move on to the exponent. First, we will need to read the exponent as a normal unsigned integer. Here, we get 137. Remember that we have a bit to store the sign of the number, but we don't have any bits to store the sign of the exponent. To represent both negative and positive exponents, the computer offsets the number. An unsigned number can be used to represent a signed number if it's used in a calculation to offset it. In floating point, exponents are stored plus 127. To recover the correct exponent, we subtract 127 from the number. Say your 8 bits represent 137. The actual value of the exponent then is 137 minus 127, which equals 10. Say your 8 bits represent 102. The actual value of the exponent is then 102 minus 127, which equals minus 25. If your 8 bits translate to 0, the actual value of the exponent then is 0 minus 127, which equals minus 127. If your 8 bits translate to 127 itself, the actual value of the exponent then is 127 minus 127, which equals 0. By this way, we can represent both positive and negative exponents without needing to assign a specific bit to represent the sign of the exponent. So let's go back and read what our actual exponent is. The 8 bits of our floating point number read to 137. In floating point system, by convention, the exponents are offset by plus 127. Therefore, the true exponent value is 137 minus 127, which equals 10. So 10 is our exponent here. The rest of the 23 bits are assigned to store a Mantissa. A Mantissa works just like a fixed point number. You start to read the first bit from 2 to the power minus 1, and you have to assume that there is always a 1 in the zeros place, followed by a fixed point by default. So though there is no bit specifically explicit in the Mantissa for the zeros place, it's on by default, and hence we should always add 1 when calculating our Mantissa. Here we can see our Mantissa is 137 by 128. Now that we have all our three parts, let's put them in the equation and get our decimal value. By working all the parts, we get our final value, which is this decimal value. The most vital point to note here is that no matter what the Mantissa is, we can vary the exponents to get a very small or very large number. To do the vice versa process, that is to convert a fixed point number into a floating point format, we first convert the decimal number into binary. Just like how converting from binary to decimal is repeated multiplication with the corresponding powers of 2, decimal to binary conversion is just repeated division. So first we go through the already familiar process of converting an integer into a binary. In this case, we get 10011. Proceeding to the decimal part of the number, we again repeat the same process with the decimal part, but this time we'd multiply by 2 instead of dividing. Why? Remember, each of the bit in the decimal portion is represented by 2 raised to its corresponding negative power. Since dividing by 2 to the power minus 1 is the same as multiplying by 2 to the power 1, we do repeated multiplication by 2 to get the binary representation of the decimal part. In this process, you first multiply the decimal part of the base 10 number by 2. Make note of the integer part of the product. In this case, it's 0. Now multiply again by 2. If your product becomes greater than 1, subtract 1 from the product before multiplying with 2 again. Repeat this process until you reach the 0. But you may not always get 0. In such cases, such as this case, continue the process until you have values for 23 bits and then stop. Now if we combine our bit string for the integer and the bit representation of the decimal part of a number, we get the fixed point binary representation. Now we need to change the fixed point base 2 number to floating point base 2. The first step in this process is to normalize our fixed point bit string. When a number is said to be normalized, it means the floating point is placed to the right of the first non-zero significant digit. So let's move our point to the right of the first non-zero bit and change our exponent accordingly. So now we know all three parts of our equation. The sign is 0 since our number is positive, and we know our Mantissa. Our Mantissa is everything that comes after the decimal point. Recall that we don't specify the 1 before the point in our Mantissa, as it's always assumed to be on by default. To get our exponent, we offset our true exponent by adding plus 127. So 4 plus 127 is equal to 131, which is 100000011 in bit string. Now we have three strings for our sign, Mantissa, and exponent, and by combining these, we get our floating point representation. Now that we know how floating point numbers work, let's move on to floating point arithmetic. Floating point addition and subtraction. In addition and subtraction, the radix point is first shifted in one of the operands such that both operands have the same exponent. Then, addition or subtraction takes place. Finally, the result is normalized. Now let's see floating point multiplication and division. First, check for 0. If none of the operands are 0, proceed to add or subtract the exponents. Then, multiply or divide the significance. Normalize. And then round the final answer. In the next video, let's see in more detail how the computer performs arithmetic and logical operations.